Hello, folks. Dr. L here. We are back with another segment. In this module, we're going to discuss some details regarding a few statistical measures of association, those specifically being the covariance and correlation metric. We're going to use a very small sample of data to run through what I think is a fairly intuitive example to understand what the covariance and correlation do, shortfalls of the covariance, and how the correlation kind of helps fill the gap in being a slightly more informative metric. Let's go ahead and start by taking a look at the data set. When I said very small data set, I was not kidding. We are going to be dealing with only 3 observations in our data set. But for each observation, we're going to measure not 1, but 2 different characteristics. First thing we're going to do, for each of the 3 individuals sampled, we are going to measure their age in years. We'll call that the Y variable, and we'll label that on the Y-axis momentarily. The second feature that we are going to measure on each individual is the number of younger siblings that the individual has. We'll call that the X variable. And it's always kind of a good idea just to sort of take a preliminary guess at presumptively what you might think the relationship would be between those 2 variables. And if you're worth saying maybe there's not that much of a relationship between them, that may be the case. Really, it depends on empirically what we see in the data. But I would suggest if you think about a child that's like very, very young, right, not even 1 year old, the likelihood that they have siblings is probably very low, specifically siblings that are younger than them. However, as individuals age, the likelihood as they get older that more siblings were born after them, well, there was more time passing, could be the case, perhaps, that the older you are, the more likely it is that you have larger numbers of siblings, maybe up to some extent. So maybe we'd expect to see a positive relationship. And in fact, in the actual data that we have here, you can kind of take note that observations 1, 2, and 3 are very young individuals, 1 year of age, 3 years of age, and 5 years of age. And observation 1, that's 1 year old, has 0 siblings. Observation 2, who is 3 years old, has 1 sibling. And observation 3, who is 5 years of age, has 2 siblings. So it kind of looks like here, as the number of years of age increase, that's associated with larger numbers of siblings on average. And to visualize this, we want to use the appropriate visualization technique, that being a scatter plot. And all we're going to do here is we're going to label age on the vertical axis, and we will plot siblings as the X variable on the horizontal axis. So our first observation 1 had 1 year of age with 0 siblings. Second observation, observation 2 in the second row, was 3 years old and had 1 sibling. And observation 3 corresponded to having 2 siblings and 5 years of age. Where again, siblings is the X value, the first number in that ordered pair with the parentheses, and the age is the Y variable, the second number. And I'll stick with that reference within the scope of this example throughout this segment. So let's go ahead. I'll take away the data in tabulature form on the right, since we have it visualized on the left. I'm not going to be too redundant here. And hopefully, looking at that information, you're convinced, at least, that this is some positive relationship that we are observing here, despite the fact that we only have 3 observations. That being the case, if we were to apply any of our measures of association, correlation or covariance, we should expect that both of those metrics would be positive, indicative of identifying the scenario, in fact, as a positive relationship. Okay, so what we're going to do in a moment is we're going to work through the exercise of computing them manually. so that we can verify our intuition with respect to these metrics. Now, the sample covariance and also the population covariance does this as well. It measures the degree of linear association between variables in a data set. But if we're dealing specifically with sample data, you may remember that we had to contend with this very small sample degree of freedom adjustment in the denominator. And that will be relevant for us today because we are dealing with a sample, very small sample at that. And the other thing we want to recall from earlier discussions is that this statistic is sensitive to the units of measurement of each variable. For example, X is measured in the number of siblings. A X bar, the average number of siblings, is measured in the same units. So if I take X minus X bar, the deviation, that's also measured in the number of siblings. Okay. However, the Y variable is measured in years, and the average Y bar value is also going to be measured in years, and years minus years are also years. However, once we take the number of siblings and multiply it by the number of years, then we get a very strange metric, and that metric is literally siblings times years. Okay, so one issue with the covariance is that it is sensitive to the units of measurement that we adhere to when measuring our data set. If we were to change, for example, from years to months, we would see that what would happen is every one of these Y values would increase by a factor of 12, as would the average. And as a consequence, that would make the entire covariance increase by a factor of 12. In fact, I'm going to ask you again at the end of the segment to redo the example and to verify that this is the case, but I will reiterate that point in a moment. Let me go ahead and just move that formula to the top of the screen so we have it easily referenceable. And let's kind of think about that. If instead of measuring age in years on the vertical axis, we measured it in months, okay, then the scale of each of the second coordinates of those points is going to change by being multiplied by a factor of 12. Right, 1 year becomes 12 months, 3 years becomes 36 months, and 5 years becomes 60 months. What we're going to see, or rather what you will verify on your own, is that this will actually cause the covariance to increase, even though the nature of the relationship hasn't really changed, right? The picture itself is not very different. Okay, it's an upward sloping positive relationship. In fact, it almost looks like those 3 points are on the same straight line, right? Linear line. And we'll talk about that point in a moment. But in terms of the units of measurement, we should be able to see here that we could choose whatever units we want. If I wanted to make the covariance really big in magnitude, I could switch maybe from months to days. Or if you go from years to days, that's like multiplying everything by 365. So the point of this is to understand that the covariance has a little bit of a weakness in its interpretability. And while it is informative in terms of the sign, if I get a positive covariance, that's indicative of a positive relationship, negative covariance, a negative relationship. The magnitude doesn't mean much. It doesn't mean much in that we could just switch from years to months to days, and we could make the magnitude of the covariance get larger and larger and larger. The correlation, on the other hand, is a little bit more of an improvement in that it's informative in kind of an additional capacity relative to the covariance. The correlation will tell us the same thing in terms of whether the relationship's positive or negative, but there's an advantage to the correlation that we're going to discuss in a moment that also gives us a little bit more information about the strength of that relationship. First property of the correlation that we want to talk about is that it actually does not depend on the units of measurement of either variable. It's a units-free metric, which right away is going to kind of remove some of the problems that the covariance metric had. It also preserves the same sign as the covariance, meaning that if there's a positive relationship, both of those metrics should agree. They should both be positive. If it's a negative relationship, they should both be negative. And in the case of no relationship, they should both be not significantly different from zero. The other nice thing about the correlation rather relative to the covariance is that the value has to be bounded between -1 and +1. Okay? And that means even if we change the units, because this is a units-free metric, it's not going to change the value of the metric between that scale, meaning that scale gives us a little bit more of a clear idea of using that metric in an absolute sense. Highest it could be is +1 in the case of the most perfect linear relationship we could have. Lowest it could be is -1 in the case of a perfect inverse or negative linear relationship. Now, the way we compute the correlation requires us first to have completed a few prerequisites. We actually need the covariance calculated, and we need the standard deviations of each of the individual variables, x and y. And you should recall from an earlier discussion that the standard deviations are measured in the same units as the individual variables, so that when we deal with this problem of the covariance in the numerator being measured in those strange units, we said that was measured in siblings times years. Well, what's going to happen now is we're going to divide by the standard deviation, which is measured in siblings for the x variable, and we're going to divide by the standard deviation of y, which is measured in years for the y variable. So the top of that fraction, the numerator, has units of siblings times years. And now the bottom of the fraction also has units of siblings times years, meaning those units will cancel out, leaving us with this units-free metric that is the correlation coefficient. And this is the Greek letter rho to represent that. Just like we kind of use the Greek letter sigma to refer to the population standard deviation and the Greek letter mu to refer to the population mean. Turns out we do not need a different Greek letter, non-Greek letter treatment for the correlation because when you divide the covariance by the product of the standard deviations, that number n-1 or n, depending on if you're using the small sample or the large sample formula, actually cancels out. So it doesn't matter if you're using the population formulas or the sample formulas when you compute the correlation metric. And let me go ahead and move that to the top of the screen. And let's now think about how the absolute scale of correlation helps us with identifying the strength of relationships. If we have a correlation of +1, this is going to correspond to what we call a perfect linear relationship between x and y, where you could think literally we make a scatter plot and all of the data points fall on the same upward sloping straight line. Maybe indicative of what we're seeing on the screen now. At the other end of the spectrum, the correlation could be equal to -1, and that will be indicative of a perfect negative linear relationship between x and y. If we were to plot that situation, we would see a downward sloping straight line scatter plot, where again, all the data points fall on that same downward sloping straight line. Now, the closer we are to a magnitude of 1, either in the positive or negative direction, the closer we are to dealing with a strong relationship. The more we are towards the ends of that spectrum at the bottom of the screen, the closer we are to perfect linear relationships, either on the positive end or the negative end. However, if the correlation value is closer to 0, and in this picture, it looks like the threshold is 1/2, but the story is slightly more complicated than that. I will discuss that at the very end. Okay, but the closer the correlation is to 0, the more indicative that metric is of X and Y not having a linear relationship with each other. And again, this could happen if you have a flat linear set of data. A flat means you change X and Y does not change. That may look like it's a linear relationship, but if it's flat, it is actually no relationship. You could also have a scatter diagram where there's just no clear way to fit any sort of line to the data, which would probably be associated with a correlation close to zero. Now, with that being said, okay, again, the correlation measures the degree of linear relationship, just like the variance, meaning it inherits the sign of the covariance. Literally, the way we calculate the correlation relies on us taking the covariance in the numerator, which could be positive or negative, and then we divide by something that has to be always positive in the bottom, right? Standard deviations are always positive, or at least non-negative. Could be zero if all your data values are constant. But they can't be negative because we square all the deviations before we average them out and take the square root. Now, the improvement of correlation over the covariance is that it doesn't just capture the sign of the relationship, it also tells us something quantitatively about the strength of that relationship. And again, this is stemming from really it also being a units-free metric. We can't just change the units and cause the scale of that metric to change. It's bounded on this -1 to +1 interval. Okay, now, if we recognize, back to our example, that the data on the left actually does fall on the same straight line, okay, meaning that data exhibits a perfect positive, right, upward sloping linear relationship. It's on the same exact line perfectly. Then we hopefully should know now, looking at the bottom spectrum on the screen, right, green and red, what value the correlation should have when we compute it. It's a perfect positive linear relationship. Okay, so we're going to calculate it mathematically in a moment using the data. But if you actually look at this picture carefully, we can quantify with a fair amount of certitude what is happening between the X variable and the Y variable, right? When we move from observation 1 to observation 2, the X variable goes up by 1 and the Y variable goes up by 2. Right? So your delta Y over delta X, delta Y is 2, delta X is 1. That's the same thing that happens when we go from the second observation to the third observation, right? Siblings goes up by 1, years of age goes up by 2. So for every 1 unit increase in X, we're getting a 2-unit increase in Y. And that actually measures very directly the slope of that blue line. You may also remember the equation of a line involves us measuring this vertical axis intercept, which has a value of 1 in the y equals mx plus b form. So the equation of that line itself, on which all of the data fall, is actually y equals 2x plus 1. And you can verify that if you plug in any number of siblings for x, like you plug in, we have zero siblings, then y is going to be equal to, well, we must be 1 year old in the data set. If we plug in 1 sibling in for x, then y is going to correspond to being 3 years old in the data set. The data is perfectly linearly related. In this case, what should the correlation be? Well, as we just discussed, it better be equal to +1. And we want to wrap up this segment as an exercise to actually manually compute the correlation and verify that this is indeed the case. Okay, so we know what to expect. Let's go through and verify mathematically by computing the correlation. Maybe easier to reference the data in tabulature form here. And what we're going to need to do to compute the correlation, I mentioned there's a few prerequisites. There's actually 4 prerequisites. First thing we're going to need to compute are the sample means for X bar and Y bar. That is the average number of siblings and the average age in the data set, respectively. We're going to need that first in order to be able to calculate the covariance. Okay, the next thing we're going to do before we even calculate the covariance is we're going to take the other low-hanging fruit, which is we're going to estimate the standard deviation of the number of siblings and the standard deviation of the age. Once we got both of those things done, then I think the next natural step is we will compute the covariance using our results from 1 and 2. Really, just from 1. And in step 4, we're going to use our results from 2 and 3 to then go ahead and compute the correlation by taking the ratio of the covariance calculated in step 3 to the product of the standard deviations computed in step 2. Okay, so first thing, let's go ahead and calculate the sample means for each value x and y. If we add up the number of siblings, 0 plus 1 plus 2, that is 3, divided by 3 gives us an average of 1 sibling across that data set. And the average number of years of age, we add up 1 plus 3 plus 5, that gives us 9, divided by 3 gives us an average age of 3. I'm going to go ahead and store those values there so I don't forget about them while we use them in the other calculations. Next thing we need to do is compute the sample standard deviations for each variable, x and y, which means we're going to go ahead and add up the square deviations from the mean. Since we have 3 observations, we're going to be adding up 3 terms before we average them by dividing not by 3, the number of observations, but by n minus 1. We have that degree of freedom adjustment here. Okay, in each of the terms and parentheses that are getting squared, the first thing we're going to do is we're going to substitute the average value for x relative to which we are measuring all of the deviations. So 1 goes in here, 1 goes in here, and 1 goes in here. Okay, the next thing we have to do is plug in the actual x values for each of the 3 data points. Data point 1's x value was 0 siblings. Data point number 2, observation 2, had 1 sibling. And observation number 3 had 2 siblings. So 0, 1, 2, 0, 1, 2. Very easy. And then we get to simplify what's going on up in the numerator. We got -1 squared plus 0 squared plus 1 squared, which gives us 2 up top, 2 in the bottom, leaves 1 underneath that square root. Square root of 1 is 1. And hopefully this makes sense that the standard deviation of x is 1 year. If you look at the 2 siblings that aren't the average sibling, how far on average away are they from the average? They're each 1 year above and below the average. So I think hopefully that metric makes a little bit of sense here. We also want to go ahead and do exactly the same thing for our y variable, that y variable again being age. So we're going to wind up adding up for 3 data points for the y value here, the square deviations, and then averaging them by dividing by n minus 1, 3 minus 1 here. And instead of plugging in x bar into each of those terms, we're going to substitute our value of y bar into each of those terms. Y bar goes in, y bar goes in, y bar goes in. Now we are measuring the deviations relative to the mean value of y, the average age. And again, we'll go ahead and do this piece by piece first. We'll plug in the average age for observation 1. Boom. Then we'll plug in the average age for observation 2. Boom. And then we'll plug in the average age for observation 3. Boom. Okay, from here on out, a little bit of math. We wind up with -2 squared up top plus 0 squared plus 2 squared, all divided by 2 and all of that underneath that radical, which gives us 8 divided by 2 underneath the radical, which is 4, and the square root of 4 is 2. So we've completed step 2. And what we can do now is calculate the covariance. That'll be our step 3. Okay, the covariance formula is a little bit different than the variance formula. And I realize I did not have the variance formula up at the top of the screen here, but remember, the covariance of something with itself is the same thing as the variance of that thing. So if we were to plug in X and X instead of Y over here and Y over here, that would be the formula for the variance. And we're measuring the squared deviations, X minus X bar squared. So we kind of do have the variance formula up there. It is a special case of the covariance formula. To calculate the covariance, what we're going to need to do here is we're going to look at the pairs of XY values for each observation, observation 1, 2, and 3. We're going to multiply for each observation the deviation from the average for each variable, and then we'll average the product of those deviations out by, again, dividing by that n-1 factor. Okay, first I will plug in my deviations relative to the X mean of 1. So again, we're going to see here, X bar goes in there, X bar goes in there, X bar goes in there. Then we'll plug in our deviations relative to the Y mean of 3. Okay, so what's happening now? Well, we took Y bar, we plugged it in here, we plugged it in here, and we plugged it in here. Okay, what is going in front of each of those values? Well, just like with the standard deviation, when we measure the deviation for the mean, we'll start maybe here consistently with our X values. 0 goes in here, boom, boom. 1 goes in here, and 2 goes right there. So those are our deviations from X, and then we want to multiply those by the deviations from Y. So the first observation's Y value is 1. That goes right here. Second observation's Y value is 3. Boom, boom. And last but not least, we have our value of the 5-year-old individual right there. Okay, so notice the first term gives us -1 times -2, which is +2. The middle term is 0, and the right term is +2 times +2. Or sorry, +1 times +2. So we have 4 up top, 2 in the bottom, which gives us a covariance of +2. And because this measurement is positive, that is again confirming that we do have an upward sloping relationship, which we saw clearly in the scatter diagram had to be the case. In fact, it was a perfect linear relationship. The data points all fell on the exact same straight line. Now, that being said, okay, the metric is dependent on the units of measurement. So when we say this is 2 equal to the covariance, what are the units? It's 2 sibling years. Okay. What are we going to do next? Well, we're going to take that metric measured in sibling years. We're going to divide it by the standard deviation of siblings measured in sibling, as well as standard deviation of years measured in years, and that will cause those 2 units to cancel out. Okay, so our last step here is to go ahead and use the formula for the correlation coefficient, and we're going to plug in 2 for the covariance, 1 for the standard deviation of X, and 2 for the standard deviation of Y. And as we expected, the correlation tells us that we have a perfect positive linear relationship between the X and the Y variable in this example. Okay, you should also, again, verify on your own that if we were to go ahead and change the age column to being measured in months or days, and you went through steps 1 through 4 again, you should verify that the covariance will change, but the correlation will stay the same. Okay, so something to experiment on your own there. All right, we had this positive linear relationship. The correlation correctly identified this as such. Okay, and again, make sure you verify that if we did change the units of measurement, let's say to months, that you would still get a positive one value of the correlation, but you will see the scale of the covariance actually increases by that factor. Okay, now let me go back to the original data here. And I want to think about doing something else. I want you to imagine taking maybe the top data point up there, the third observation, and let's change it just a little bit so it's not perfectly on the same line as the other two observations. Let's take it away. Let's move it over. So instead, that individual is 5 years old, but has, let's say, 3 siblings. Note now that the data set no longer represents a perfect linear relationship, but it is still a fairly obvious positively sloped relationship. So what I would like you to do on your own is go back again through steps 1 through 4, but with these 3 values instead of the other 3 values. There's only one data point you'll change, but you'll realize that that change winds up affecting not the average age, but it will affect the average number of siblings, which is then going to affect the standard deviation of the number of siblings, which is going to affect things, some of the other metrics that depend on that. So you should go back through steps 1 through 4 again, but try it with this data set. And you should notice when that happens, the correlation should decrease relative to the value of positive 1 that we found when all the data points were on exactly the straight line. The follow-up to that will be to move the data points even farther away from being on the same straight line, and you'll notice the correlation starts to drop even more towards 0. Before we wrap up here, a real quick note on statistical significance. Sometimes you may calculate a correlation or even a covariance, but I'm going to talk about this with respect to correlation. And you may get a correlation fairly close to 0, like 0.1 or 0.05. You might get a very small correlation. And it could easily be the case, as we will discuss in later segments, that the reason why the correlation isn't exactly 0 maybe is coming from some sort of sampling error or measurement error, noise, if you will. Okay, but it could be the case that really the correlation actually is 0, but we just sampled the wrong observations to be able to see that feature. Meaning there might be no relationship. The correlation may actually be 0, but when we compute the metric, it might be just very close. And if it's very close, that could be just because of randomness in the data. And we want to make sure, to be safe, that we actually have a valid correlation value. When we find a relationship of association using correlation, we want to make sure it's actually there or not. So to be safe, for the moment, we're going to use the following ad hoc significance check to check the significance of the correlation statistic to see if it is significantly far enough away from 0 to say that we actually have some strength in the relationship. Remember the spectrum earlier, I kind of threw up the values of 1/2, positive and minus as reference values, but the actual threshold is more consistent with what I'm about to show you here. And the correlation is only going to be statistically significant if its magnitude, its absolute value, is greater than 2 divided by the square root of the number of observations. This is an approximation, but it's a pretty easy ad hoc rule to apply here. For example, if you had a data set instead of 3 observations with 400 observations, okay, then I could plug in n equals 400 into that calculation, 2 divided by the square root of 400, right? What's the square root of 400? It's 20. So we get 2 divided by 20, which is 1 divided by 10, which is 0.1. And what that implies is, in order for us to say we have a significant relationship statistically, that is different than 0, no relationship in terms of the correlation's value, the magnitude of the correlation coefficient rho would have to be at least as big as 0.1. If we got a correlation of 0.2 positive, we could say, okay, we have a positive linear relationship. It's significant. Maybe not super strong, but it is significantly different than none. If we got a correlation of like negative 0.15, well, the absolute value of that's also bigger than 0.1. So that would be a statistically significant correlation in the negative direction, even though maybe it isn't very strong. Okay, so there's a difference between significance statistically, okay, and where that kind of that threshold is for a relationship being non-existent or existent. There's also a difference between statistical significance and practical significance, but we'll come back to that idea in another discussion. So we've argued here very specifically for a sample size of 400 observations that the correlation coefficient will be statistically different than 0, provided its value was larger than that threshold of 0.1 in magnitude, in either the positive direction or the negative direction, implying that we have enough evidence in our data to say that the correlation is not equal to 0. There is some linear dependency between the x variable and the y variable. So hopefully that cleared things up regarding measures of association, and I hope to see you in future segments. Take care.